Okay, so we're going to start with a review of the 2 rules of op amps. Then we're going to cover inverting and non-inverting amplifier circuits. And remember the formulas that went along with those. Then we're going to do a lecture, and we're going to talk about 3 more types of op amp circuits. We're going to talk about voltage followers, which are also called buffers. We're going to talk about difference amplifiers, and we're going to talk about summing amplifiers. Okay? So we'll talk a little bit about what each one of those things does, what they're good for, why we might use them, and then how they actually work. And again, we'll see that the 2 rules of op amps can guide us and explain what's going on in each of those circuits. Okay? So, any questions before we get going? All right, then let's start with the review. So we talked about the 2 rules of op amps. Anybody remember the first rule?
The voltages are the same.
Yeah. The voltages are the same at the inputs. And what about the second rule?
No clue.
No current flows with the amps. It's perfect. Okay, cool. And we use these 2 rules to talk about 2 different amplifier circuits. So we talked about an inverting amplifier circuit, and that one looked like this. We had our input here, and then we had a resistor, and this resistor was connected to the inverting terminal. Okay? So when the input goes to the inverting terminal, it's an inverting amplifier. All right? And we call this resistor R-in for the input resistor. Then we had our output here, and that output connected back to our input and had a resistor there, and this was called the feedback resistor, RFB. Okay? Then we had our non-inverting terminal, and that was connected to ground, right? So we did some analysis here, and we figured out that there was a relationship between the input voltage and the output voltage. We said that we used our 2 laws of op amps, and we figured this out, and we saw that there was a formula we could use. We said V out equals V in times R feedback over R in. Okay? So if we had a 10 kilo ohm feedback resistor and a 1 kilo ohm input resistor, then our output voltage would be 10 times bigger than our input voltage. And we called this the gain. This is how much bigger the output was than the input. We could find the gain in a couple of different ways. We could calculate it using this formula, or we could actually measure it. If we measure the output voltage and divide that by the input voltage, that also gives us the gain. Okay? So, any questions? Yeah.
That's all like negative, right?
Yes, thank you. So since this is the inverting amplifier, there is a negative sign here. So the gain is negative. That means that if you have a positive input voltage, you get a negative output voltage. Thank you for reminding me.
And
So
gain numbers are also expressed as negative.
So yeah, the gain is for a inverting amplifier, the gain is negative. Yeah. So if you have a positive input voltage, you get a negative output voltage. The sign is inverted, and that's why we call it an inverting amplifier. So any questions about that? Okay, cool. So then, let's talk about a non-inverting amplifier. With the non-inverting amplifier, the circuit was similar, but there were a few changes. So, here, the inverting input was connected to ground through this resistor, and the non-inverting input was connected to our signal. So, what we found in this case was that V out equals V in times R feedback divided by R in plus 1. So here, this whole quantity was our gain.
A second, the gain in parentheses, right, before we multiply that.
Yeah, so put parentheses around there like that. Yeah. So in this case, the gain is positive. So when you have a positive input voltage, you get a positive output voltage. The sign is not inverted, so this is a non-inverting amplifier circuit. Okay? So, any questions about that? Okay, cool. Oh, I'm sorry. Okay. So, today we're going to talk about three other types of op amp circuits. We're going to talk about a voltage follower, which is pretty much the simplest op amp circuit that you can make. We're going to talk about a difference amplifier, and then also about a summing amplifier. Okay. Anybody need a few more minutes on this stuff? Okay. All right, so let's talk about a voltage follower circuit. So let's talk about what's going on here. So we can use our two rules of op amps to analyze this circuit. So we know that we've got V in attached to the non-inverting input, So what is going to be the voltage at the other terminal, the inverting input? Same thing, right? That's what the rule number 1 says. So we know that we have V in right there. But now this is connected by a wire straight to the output. So what is V out going to be? The same. So V out equals V in. Okay? So that's why it's called a voltage follower. The output voltage follows the input voltage. This is also called a buffer because it basically what happens is that we said that no current flows into the input, right? So no current is flowing into this positive, this non-inverting input terminal. So this gives us some insight into why these circuits might be useful. Imagine that you had a very, very small or very, very weak signal. You know, something that is coming out of an instrument that's very sensitive and just cannot provide very much signal, okay? You would not want to have that going into like a small resistor, because that resistor might drain away all of the signal that you're trying to measure. Okay, so if you have that very weak signal going into this, connected to this non-inverting input, this non-inverting input has a very, very high resistance. That means that it draws hardly any current at all, right? So it's not going to affect your very weak signal. Okay? So this circuit can provide a buffer, sort of a guard between your weak signal and the rest of your circuitry. Okay? So that's why it's sometimes called a buffer circuit. Okay? So these circuits, this circuit can be used to protect very weak signals. Another way to think about it is that we know that we're not getting any voltage gain here, right? The voltage out is the same as voltage in. So when we've made other amplifiers where we don't get any gain in voltage, what did we gain in? Current. So you could also think of this as a current amplifier. Okay? It draws almost no current at all, and the output can have quite a lot of current coming out. So you could see this as a current amplifier circuit.
Because it runs the current through the rails, right?
Right. Yes, exactly. This op amp is called an active component because it has power that it draws from other sources, from the power supply. Other components like resistors, capacitors, diodes, those types of components that don't have power supplies attached to them, those are called passive components. Transistors, op amps, things like that are hooked up to power supplies are called active components. Okay? So this is an active component. It gets its power from an external source. So this is a voltage follower or a buffer op amp circuit. Any questions about that? Okay. Then I'm going to move on. Anybody need a few more minutes on this? Yeah.
So you could take a very low, like I said, a very weak signal.
Mhm.
It's going to have a very low current to it, but basically then use it to drive something that, an LED or something that takes 20 milliamps. or
Yeah.
whatever.
Yeah,
You
exactly.
could then basically use it to drive that. Even
Right.
though the original signal may not have had the current to drive the LED, but it had the voltage.
The indicator.
Now
Yeah.
you can.
Yeah. Yeah.
Okay.
Or right, exactly. You could drive other components in a circuit that require more current. Yeah.
Thank you.
Mm-hmm. Other questions? Okay, cool. So let's talk about another op amp circuit, which is called a difference amplifier. Okay? So difference amplifier circuits work to, they have two input signals, and they work to magnify or amplify the difference between these two inputs. Okay? So one input is up here. Another one is there. Okay, so let's do an example with this type of circuit. So let's say that we had 9 volts here, and we had 8 volts there. Okay? Let's look at what this circuit would do. So we have a difference of 1 volt. Okay? So that's the difference between these two inputs. Now let's look at the bottom part of this circuit first. So we've got 9 volts, and then we've got a 1 kilo ohm resistor and a 2 kilo ohm resistor. These resistors are in series, and they're connected to the op amp, but we said that the op amp draws no current, right? So the op amp is not really affecting this series circuit. So really, this bottom part of the circuit is just behaving like 2 resistors in series. So what's a special name that we use for 2 resistors in series like that? Voltage divider, exactly. So we remember that if each resistor has half the total resistance, each one gets half the total voltage. In this case, the top one has 1/3 of the total resistance, right? The total resistance is 3 kilo ohms. Top one has 1/3, the bottom one has 2/3. So the top one gets 1/3 of the total voltage. So it has 3 volts across it, and then the bottom one gets 2/3 of the total voltage, or 6 volts across it. Any questions about that part?
Do that one more time.
Yeah, so basically we've got a situation like this. We've got a voltage divider, we've got 9 volts up here, 1 kilo ohm and 2 kilo ohms. Okay? And we remember that with the voltage divider, each one of these resistors gets a portion of the total voltage. So if they each had half of the total resistance, they would each get half of the total voltage. In this case, the top one has 1/3 of the total resistance, so it gets 1/3 of the total voltage. So it gets 1/3 of 9, which is 3 volts. Now the bottom one has 2/3 of the total resistance, so it gets 2/3 of the total voltage. 2/3 of 9 is 6 volts. Okay? Questions about that? Making more sense?
Yeah.
Cool. All right, so we know that we have 0 volts here, and then we go up by 6 volts. So we have 6 volts right at that point there, right? Okay. So now let's look at what's happening at the top. What voltage do we have at this inverting terminal? 6 volts, exactly. That's from the first rule of the op amp, right? We know we have 6 volts down here, so we must have 6 volts up there too. Okay? Yeah.
So we start with the non-inverting one because it doesn't have the feedback resistor, and the feedback resistor allows the top one to kind of adjust to match. Is that why we start there?
Right.
To determine what they both are?
Right, exactly.
Okay.
Exactly. So we got 6 volts up there. We have 8 volts on the other side of this resistor, so we know that we have a 2 volt difference across this resistor. Okay? So we know we have 2 volts across a 1 kilo ohm resistor. How much current do we have? 2 milliamps. Yeah. Remember, any voltage across a 1 kilo ohm resistor gives you that many milliamps. So 2 volts across 1 kilo ohm gives you 2 milliamps. Okay. Yeah, exactly right. So this current is flowing that way. We know from the second rule that none of it flows into the op amp, so all of it must flow up here through this resistor. So you must have 2 milliamps flowing through there. So how much voltage do we have across that resistor? 4 volts. Right? Voltage equals current times resistance, so that's 2 milliamps times 2 kilo ohms. It comes out to be 4 volts. Okay? So, and we're going down by 4 volts here. So we started at 6 volts, we go down by 4, we end up with 2 volts on the output. Okay? So we had a difference of 1 volt on the input. We end up with an output of 2 volts. So what's going on is that this circuit looks at the difference between the input voltage and it multiplies it by sort of the same factor that the inverting amplifier uses. It multiplies it by R feedback over R in. So in this case, we would have a gain of 2. So we have a gain of 2 and a difference of 1 volt. So we get an output voltage of 2 volts. Okay? So we could set our gain to be higher by choosing different resistors here. If we could choose a gain of 10 or a gain of 100. And then we could multiply the small change in input by that gain. Okay? So this is really an important circuit for measuring the difference between 2 signals, especially a small difference between 2 signals. So you could use this for things like an EKG. You guys have heard of EKG machines before? Those are the machines that are in hospitals that measure your heart rate. And what they're really doing is that they're measuring the electrical signals that are being sent that tell your heart to contract. Okay? So first of all, those signals are very small. So they're small and they're weak, and also they might have a lot of common mode voltage. So basically, they might be quite large to start out with. So you might have like, 5 volts here and 5.01 volts up there, or something like that. So if you just had a standard amplifier and you were amplifying the entire signal, then what you would get is you get, if you multiplied it by 10, you get a 50 volt signal. But all you really care about is the difference between these two, right? You don't care that they're at 5 volts or 10 volts or whatever. What you care about is the difference between them, like the difference between the voltage on one side of your heart and on the other, because that's what's causing it to beat, right? So you would use a circuit like this, and this gets rid of the common voltage, right? This didn't care that one was at 8 volts and the other was at 9 volts. All it cared about was that the difference between them was 1 volt. Okay, so if this had been at 99 and 100, this still would have given us the same output. Okay, so it's really just looking at the difference. So this is good at measuring small differences between signals. Okay? So this happens, like I said, in the biomedical field. It also happens a lot in sensor type settings where you are measuring a signal coming out of a sensor, either for like a seismic measurement or something like that, or there are other instruments called strain gauges that are used often in engineering and things like that. Oftentimes these create small differences that you have to measure. So you could use a differential amplifier like this to just look at the difference between two signals. Yeah?
So the two input resistances are the same, and the feedback and the ground resistors are the same.
Yes.
We always do that
Yes.
way?
You always do it that way. And the reasons for that go a little bit beyond the scope of what we want to discuss here. Yeah.
Don't care about that, I just want to know it.
But yes, you're absolutely right. We always match the input resistors and the other resistors, and it has to do with the circuitry inside the op amp and making sure that all of that balances out. Yeah.
Output voltage always will be positive, right?
No. So what we say is V out equals R feedback over R in times V2 minus V1. So it looks at the difference between these two signals. So if V2 is bigger, then the output will be positive. If V1 is bigger, then the output will be negative. Okay. So here, the gain is R feedback over R in, but now it's multiplying by the difference between these two input signals. Okay. Questions about that? Okay. So the last type of circuit that I want to talk about tonight is the summing amplifier. Okay? So what this does is that it takes several different input signals and it adds them together. So this could be used for something like a mixing board in acoustics, in music. Right? You've got several different musical tracks that you want to combine. Maybe you want one to be louder and the other one to be a little bit softer. You would use a summing amplifier for something like that. Okay, so you would feed each track to a different input, and then you could adjust the gain for each track. You could adjust the gain for the entire combination of tracks, and then the output would be the sum of all those different inputs. Okay? Yeah.
So is this how we would put an intelligent signal into a carrier wave, for example?
It's very similar. So, right, if you had well, it depends on what type of encoding you were wanting.
Yeah.
So,
I'm sorry, I don't mean to
yeah.
derail you. I apologize.
No, that's fine. So, it would be a little bit different. So if you were talking about AM, that would be amplitude modulation. That would be more like multiplying the two signals together.
Okay.
If you were talking about FM, then that would be more like shifting the signals. So this would not exactly be like either one of those two.
Okay.
It might be used for other types of encoding.
Okay.
Yeah. So the way that these circuits are constructed, it's sort of like several different inverting amplifiers put together. Okay? So you guys remember that an inverting amplifier looks like this. We've got the non-inverting terminal connected to ground. Got our output here, and then we have feedback resistor. And then we have an input resistor. Okay, so let's say that this was a 10 kilo ohm resistor, and this was a 1 kilo ohm resistor. Okay. Now say that we had, let's see, 0.5 volts right here. Okay. So we already talked about how inverting amplifiers work, right? We talked about this last time. We know that we have 0 volts here, so we have 0 volts at the inverting terminal. We've got half a volt on one side of the resistor. We've got 0 volts on the other side. So we have half a milliamp flowing through this 1 kilo ohm resistor, right? So we've got half a milliamp flowing down there. So the total current flowing through here would be 0.5 milliamps. We multiply that by 10K and we get a 5 volt output, right? So that's what would happen if we had an inverting amplifier, right? So a summing amplifier is very similar, except we add more of these input resistors, and they can be different values. So maybe this one is a 2 kilo ohm resistor, okay? Now with this 2 kilo ohm resistor, we could have a different input voltage also. Maybe we have 3 volts there. So So now we've got 3 volts on one side of a 2 kilo ohm resistor. We've got 0 volts on the other side. So that means that we have 1.5 milliamps flowing through it. Okay? So this is now contributing 1.5 milliamps going this way. And we could have yet another input resistor also. Okay? So maybe this third input resistor has a value of 5 kilo ohms. Okay? So, and say this one had an input voltage of 2 volts. Okay, so now we've got 2 volts across 5 kilo ohms. That comes out to be 0.4 milliamps flowing through there. Right? So then this contributes 0.4 milliamps going that way. So basically the way that we analyze this is that we look at what would happen with each one of these by themselves. Okay? So if we just had this first one, then we would have an output voltage. We said 0.5 milliamps times 10 kilo ohms. That would be an output voltage of minus 5 volts. If we only had the second one, we would have 1.5 milliamps. So that would be an output voltage of minus 1.5 volts. Right? And then if we just had the final one, then that would be an output voltage of 4 milliamps times 10 kilo ohms. So that would be an output voltage of minus
40.
It's 0.4 milliamps, so it would be minus 4 volts, right?
Yeah.
So, and I'm sorry, this one would be 15 volts, right? Yeah, so 15 volts. Okay, so basically, we could have found this out just by looking at the individual gains for each one of these, right? The first one has a gain of 10 over 1, so that has a gain of 10, right? 10 times 0.5 is like minus 5, right? The second one has a gain of 10 over 2, that's a gain of 5, so 5 times 3 is 15. The third one has a gain of 10 over 5, so that's 2. So a gain of 2 times 2, that's 4. So each one of these individual outputs could be determined by looking at the individual gain times the individual input, right? But what we see is that the total current flowing through this resistor is the sum of all of these currents. So the total current through here is 0.5 plus 1.5 plus 0.4. So that is a sum of 2.4. And 2.4 times 10 is a total output voltage of minus 24 volts. Okay? So you'll notice that that is the sum of all of these individual outputs. So 5 plus 15 plus 4 comes out to be 24. So that's why we call this a summing amplifier, because the output is the sum of all of the individual outputs. Okay? So remember I was saying we could use this if like a we could use this to mix audio tracks together, right? If we wanted to do that, we would connect one audio track to each one of these inputs. We could add more inputs also if needed. And then instead of just having a fixed resistor for each one of these, we could have a variable resistor. So that would change the volume on each of these audio tracks, right? Less resistance would mean more gain, so that would be a higher total volume, or higher volume for that track. And then we could have an adjustable resistor here as well. And if we change that, that would change the gain on all of the tracks. So this could be like the total volume for the entire thing, okay? So this is how audio boards were constructed for a long time. Recently, they've been shifting more and more to digital processing. But if you're talking about analog audio mixing, this is pretty much how it's done. Okay? So, questions about that? Okay, so that's a summing amplifier. So that's really what I wanted to talk about for the lecture today. The lab is not much different than what we talked about in lecture. You're going to build one of each of these circuits, and you're going to for the buffer, you're going to draw the input and the output. For the other two circuits, you're just going to show the gain, the input, the gain, and then the output. Okay? You're going to do the actual and the calculated gains on the final circuit here. So any questions about that? Okay, then I will take roll and I'll let you go.